So in order to do exact equations to solve them, you have to know a little bit about partial derivatives. So you learn a lot about these in a multivariable calculus course, but to solve exact equations, you don't need to know a whole lot about them, and I'll explain it all here. So this symbol here isn't actually me poorly drawing it, it's actually the partial symbol. It looks kind of like that. And so this is partial x, like this is d dx, so it's a partial derivative with respect to x, and this one is a partial derivative with respect to y. So the way they work is the partial derivative with respect to x takes the derivative of something with respect to x, treating y as a constant, and the partial derivative with respect to y takes the derivative of something with respect to y, treating x as a constant. So I'll show how those are a little useful here. So previously, right, I had this function f of x comma y equals 7x squared y cubed plus sine y minus e to the x equals a constant. And when I took the derivative d dx of f of x comma y, that was equal to this thing, and I had these two pieces. I had this 14xy cubed minus e to the x, and I also had everything else that was multiplying y prime, the 21x squared y squared plus cosine of y. So here's where these partial derivatives come in handy. If I take the partial derivative of f with respect to x, all right, that is the partial derivative of this whole thing here. So I'll write it again. So it's 7x squared y cubed plus sine of y minus e to the x. All right. So if I take the derivative and I treat y as a constant now, so I essentially never take the derivative of y, I'm only going to worry about the x's. So what's going to happen is I have the 7x squared y cubed. It's no longer a product rule. I just have to worry about the x squared. So again, the 2 pops down. We get 14x to the 1 first power y cubed. So I get 14x y cubed. The next piece, I have partial x times sine of y. And since y is being treated as a constant here, this is sine of a constant, it ends up being 0. Then the last bit, I have partial x applied to negative e to the x. So that has an x in there, so it's going to be minus e to the x. All right. If I do partial y of f of x comma y, well, that's partial y of the same thing. 7x squared y cubed plus sine of y minus e to the x. Okay, that's going to equal, so partial y, I don't care about the x squared, it's like a constant, I only care about the y cubed. So take the derivative, we're going to get the 3 times 7, so that's the 21. X squared is a constant, so I just rewrite it. And then y cubed turns into y squared. And there's no y prime term. That's the big difference here. All right, so then the next term I have is partial y, sine of y. Well, that's going to be plus cosine of y. And again, no y prime term. Then I have partial y applied to negative e to the x. Well, that's just going to be minus 0 because the e to the x doesn't have any y's in it. Now, if you look carefully, this piece here, this 14xy cubed minus e to the x, that's actually this piece right here, the first bit of the d dx of f of x, y, x comma y. 14xy cubed minus e to the x. There it is. And then the piece that's multiplying the y prime is actually the partial y of f. There's 21x squared y squared, there's 21x squared y squared, and there's the plus cosine of y, and there's just this y prime tagged on. So what you can do is another way to write d dx of f of x comma y is the same thing as partial f partial x plus partial f partial y times y prime. And so this is going to be really useful for us, and we're going to use that in the next video and ultimately to solve the exact equations.